Hi, I will be discussing 2-4 trees in this video. So I will be discussing the properties, searching an element, inserting an element and deleting an element from a 2-4 tree. Let's start with the introduction. Now in a binary search tree, every node contains a single value and has up to 2 children with the property that the child with the value less than the node lies on the left side and the child with the value greater than the node lies on the right side. So this is a binary search tree. And now I'll show you how a 2-4 tree is in resemblance with a binary search tree. So a binary search tree has just one value in each node, but a 2-4 tree will have up to 3 values. So it can have 1, 2 or 3 values. Like in this node, it has 3 values, 6, 8 and 10. This node has 2 values, 3 and 4. And a 2-4 tree has up to 2 to 4 children per node. This node has 3 children, and hence the name 2-4 tree. Because of this property, it gets its name. And all leaves are at the same depth. So these are the 3 properties of 2-4 tree. Now let's see how is it constructed and how the values are arranged in the 2-4 tree. So like as we saw in a binary search tree, values greater than the node lied on the right side and the values less than the node lied on the left side. But in this case, we have many values. Like we have up to 3 values in a node. So we'll have up to 4 subtrees. So if we have k values, then we'll have k plus 1 subtrees. I'll show it in the another slide how it will have k plus 1 trees. So let value ti represent the set of values of elements in a subtree ti. So all the nodes in the first subtree will have values less than the v1, and all the nodes in the last subtree will have values greater than the last value in that node. So let's see this with an example. Like in this case, all the values less than 20 will lie on the left subtree, and all the values greater than 60 will lie on the right of the subtree, and all the values that lie between 20 and 60 will lie in this subtree. So as we see, 43, 28, 31, 56 all lie between 20 and 60. Now as we move down here in this node, we can see like 43. These values are less than 43, this value is greater than 43. So this property that the values, this arrangement of values, it goes on till the last level of the tree. So let's height of a tree is very important. So now we'll see the height of 2-4 tree. It is O log n. So this is a simple proof. Let h be the height of tree with n elements. Since there are at least 2i elements at each depth, starting from the root with 0 depth up till the h minus 1th height, we'll have all the elements will be greater than equal to the sum of the elements at every level. So that will sum up to 2 to the power h minus 1. Therefore, our height will be less than equal to log of n plus 1. Hence, our height is O log n. Searching an element. To search for an element x, we start from the root. For a node consisting of values v1 to vk, there are 4 possible cases that as we iterate through the values of a node, we can find the value. But if we don't, let's see, if we find the value, then we are done. But if the value is less than v1, then we recursively search for the value x in the subtree to the left of v1, because we know that all the values that lie in the leftmost subtree, that is to the left of v1, are less than v1. So if there is a possibility of x to be in this 2-4 tree, it will lie in that subtree. But if x is greater than vk, then we recursively search for x in the subtree to the right of vk. And if x is between vi to vi plus 1, then we recursively search for x in the subtree between vi and vi plus 1, because all the values that are between vi and vi plus 1 will lie in this subtree only. So similarly, the possibility of x being in the subtree will only be possible if it lies in that subtree. At the max, we'll have to traverse all the nodes for the entire height of the tree, and each node has at max 3 values. So our search will take O3h time, that is O of h. That will be O log n. As we discussed, the height is O log n. Let's see this with an example. If I say that I have to search for element 15, So let's see, we start with the root node. 15 is less than 20, so it will lie in this left subtree. We move down, we look at the first value 8. 15 is greater than 8, we move to the next value. 15 is greater than 12, we move to another value, next value. But 15 is less than 17, so if 15 lies in the subtree, it has to lie lies in this 2-4 tree, then it has to lie in the subtree between 12 and 17. So we move down. We look at 13 and 16. 15 doesn't lie in the subtree. So in this example, you can see that we had traversed the whole entire height of the tree, but we didn't find the node. So if we traverse the entire height of the tree and we reach the leaf node level, but we didn't find the element, then the element doesn't lie in the 2-4 tree. Similarly, if we would have searched for 13 until this point, uh, we'd have moved down and we'd look at the values in this node, and we'll see that 13 is existing in this 2-4 tree. Now we'll see how to insert an element in our 2-4 tree. Insertion. So in insertion, the procedure we follow is that we insert new element at the leaf at an appropriate position. So if the number of elements in that node are less than 4, we are done. We can simply add that value in that node. But if we add a value to a node and the elements and the number of values in a node becomes 4, then we are not allowed, because in a 2-4 tree we are only allowed to have up to 4 values. So we split up the node by sending one of the middle elements of the node one level up and adjust positions of the other elements accordingly. So let's see with an example. We start with inserting 4. So initially we don't have anything, so we insert 4 in a node. Now we have to insert 6. We insert it in the root node. We add it with 6. We add it with 4. So now in this node we have two values, 4 and 6. Now we have to insert 12. So in this node we can add 12 to this node. Now we have got 3 values in it, and we are allowed to have 3 values. Now we insert 15. So if we had insert 15 in our root node, we get 4 values. We were supposed to have up to 4 values. We were allowed only 3 values in our 2-4 tree. So this is an overflow. Now we'll have to split the node. So we can split the node by sending either of the middle elements. We can either send 6 up or we can send 12 up. So these are the two trees we obtained. Now, as we can see, if we send 6 up, we move 4 to the left subtree and 12 and 15 to the right subtree, so that the property that 4 is less than 6 lies on the left side, and 12 and 15, that these values that are greater than 6 lies on the right side. But why didn't we move 4 and 15? So if I had have moved 4 up, then all the values, that is 6, 12 and 15 are greater than 4. So we'll have just one child with one node having 3 values, but one child, that's not allowed. 2-4 tree cannot have one child. Similarly for 15, 4, 6 and 12, all these values are less than 15. So we won't be able to do that, because then there'll be just one node with the values 4, 6 and 12, and one child is not allowed in our 2-4 tree. So considering that we moved 12 up, now we have to insert 3. We move to the root node, we see the value 12. Okay, so now we have to insert 3. So we see as 3 is less than 12, we move to the left subtree. Now we just had 4 and 6 here, so we insert 3. Now in this node there are just 3 values, and we are allowed to have 3 values, so we let it be. And all the properties that the leaves are at the same height, and the properties that 3, 4, 6 are less than 12, 15 is greater than 12, and they are arranged accordingly in the left and right subtree. Now we have to insert 5. So we'll look at 12. 5 is less than 12, we move to the left subtree. We add 5 to this node. But as you can see, there's an overflow, because we have got 4 elements here, 4 values here in this node, and we are not allowed to have that. So what we'll do is that we'll move the middle element up. So we can move either 4 up or we can move 5 up. So as we see, we move 5 up here. So 5 moves above. But now, as you can see, there are 2 values here. So we'll have to have 3 subtrees. so that the values less than 5 lies in the leftmost subtree, and the values that are between 5 and 12 are in this subtree that lies in between, and the values greater than 12 here. So after moving 5 up, we'll have 3, 4 and 6, but we'll have to split this node, and we'll get 3 and 4 in this one node and 6 in this one node. Inserting 10, we look at the value 5, 10 is greater than 5, move to 12, 10 is less than 12. So it will surely lie between these two values. We move down the subtree, we see there's just one value, so we add 10 to it. Now this node has two values, we are allowed to have two values, so we let it be, and we see as all the properties are satisfied. This is the 2-4 tree that we obtain on inserting 10. Inserting 8. So again, 8 lies between, 8 is greater than 5, less than 12, move to the middle subtree, add 8 to it. Now we have got 3 values. We are fine with it. We can have 3 values in a node. But if we insert 11, so now 11 also lies between 5 and 12. Similarly, we move down, we add 11 to it, but as you can see, there's an overflow. So as we learned before, we'll either move 8 or 10 above. So that, let's see what we have done. So move 10 above here, and we divided our subtree. So now when we insert 9 to it, we see that we have got 3 values. 9 is greater than 5, but now we move to 10, 9 is less than 10. So the second subtree, the second subtree will contain the value 9. So we move down the second subtree, we add value 9 to it. So now we have got 3 values in this node, and we are fine with it. All the properties of 2-4 tree are satisfied. Now we have got inserting 7. So to insert 7, we'll see that 7 is greater than 5 and it's less than 10. So we move down here, we look at 6, it's greater than 7 is greater than 6, so we can put in this node because it has 3 values. So now we put it in this node, and then what will happen? We'll have 4 values in one node. Again, there'll be an overflow, so we'll have to move either 7 or 8 up. So as I discussed, we added our element here, there's an overflow, so we moved 8 up. But now, as you can see, we've got 5 children here, but because it's a 2-4 tree, it can have just 4 children, and it can't have 4 values for sure. So we'll have to move 1 above again, so we will either move 8 or 10 up. So we move 10 up here. So after moving 10 up here, we divided our root node that contained 5, 8, 10 and 12 into 2 parts, 5 and 8 and 12, and similarly our tree also got divided. So this is the tree that we obtain on inserting all our values. We started with 4 and subsequently we added all our elements. Now we'll see how to delete an element. Since we have constructed our tree, let's delete elements. Deletion. So to delete an element, we find the element to be deleted. That can be done by a simple multi-way search that we have discussed. So the very simple case, there are different cases in this deletion. I'll be considering 3 cases. So let's start with the case 0. That's the basic case. In this, if you imagine, if the element lies in the leaf, and there are 2-3 values in that node, and we have to delete a value, we can just simply remove that value. So if the element is a 3-node or a 4-node leaf, these are just the terminologies that are used. So 3-node is a node of a 2-4 tree that contains 2 elements, and a 4-node is a node that contains 3 elements. So removing an element from a 3-node or 4-node is quite trivial, but removing it from a 2-node would be difficult. So that would be a different case. Let's see it with an example. Like in this tree, if we have to remove 9, it's a 3-node. So we can just simply remove 9 and all the properties of a 2 4 tree are satisfied. 10 is greater than 8, all the leaves are at the same depth, and the number of values in that node also remains between 1 2 and 3. That's We have just one value, so all the properties are satisfied. So 9 gets removed, and this was the most trivial case of our deleting an element. Now let's look at another case. This the this the Starting with the case 1. This is the main case that we'll be discussing. Case 1 and case 2. Case 0 was very trivial. So case 1 is in which the element is not a leaf. Element lies somewhere in between our tree and it's not a leaf. So what we do is we remember the position of element and continue until we reach leaf containing the element successor. So we start finding the element, we find the position, we remember the position, and then we find the element successor. After finding the successor, we swap the elements, and if the leaf is not a 2 node, then we delete the element. But if it is, then that's a different case that we'll be dealing with later. Similarly, the 2 node terminology that I used here was that a node of a 2 4 tree containing just one element. It's similar to the 3 node and 4 node leaf definitions. So we have to remove 8. 8 is not a leaf. 8 does not lie in a leaf node. So what we do is we search for its successor. So 8's successor would be if we move right. But since this tree just has one node, we are done with our search. But if it would have many different levels, so what we would have done was we would have moved right once and then we'd have moved left till we reached the leaf, and then the leftmost value in that node would be the 8th successor. So in this, we moved right, we've reached a leaf, we look at the leftmost value, that is 9. So we have reached down the successor. Now what we'll do is, as I previously mentioned in our procedure, we'll swap these two values. So here I swapped these values. Now we had to remove 8. We can just simply do it. And remember, in this case 1, we are dealing with the case where after swapping with the successor, the number of values in that row are 2 or 3, so that we can easily remove it. So here the number of values become 2 and we can easily remove it, like case 0. So we just removed 8. So this is the tree we get after removing 8. On summarizing, I'd say search for the element, then remember the position of it, search for its successor, swap the elements, and then remove it if the number of values in that node are 2 or 3. Now let's move to our next case. In this case, we are discussing the case in which the element is a 2 node leaf. So it has subcases. Yes, case 2 has 3 subcases. So we'll start with the subcase 1. In this, we assume that the parent node and the sibling nodes are not 2 nodes. So let's see, we remove 9. So 9, it has its siblings, these 2 nodes, and both these nodes are 3 nodes, and its parent is also a 3 node. So what I have to say is that this is the case in which it satisfies both these properties. So what we'll be doing is we pull an item from the parent and replace it with the element that we are deleting. So we can pull down 8 here and replace it with the element that we are deleting. Let's see. So what we first do is that we remove 9. Now it creates an underflow here. We have got less than, we could have just one, we can have 1, 2 or 3 values, but we can't have no value like this. So, and it has to have 3 children. There's an underflow here. What we can do is now move down one of the parents. So we move down 8 here, and this tree that we get is still not balanced, since as you can see it has value 5, and 5 can't have 3 children, it can just have 2 children, values less than 5 and greater than 5. So This is the tree that we had, and now what we can do is, to balance this tree, we move one of the siblings value above up the tree. So as you can see, the condition that we use, that the sibling should not be a two node, is used here, because if it would have been a two node, then we'd have moved it up and there would have been an underflow. So we just move this value up here, and now this tree that we get is balanced. So 5 and 7, 3 children, all leaves are at the same depth. Now let's look at subcase 2. In this, the sibling nodes are 2 nodes, but the parent nodes are still 3 or 4 nodes. So in this case, let's see, we remove 12. So does it satisfy these properties? I guess yes. So sibling nodes 5 and 8, both are 2 nodes, both have just one value, and the parent is not a 2 nodes, it's a 3 or 4 node. In the third subcase, we'll be dealing when we have just one value in a parent. So what we can do is pull an item from parent just as before. Pull an item from parent to the empty node that is obtained after we remove our value, and then we can fuse the siblings into one node. Let's see what fusing is with an example. So we have got this tree, we remove 12. After removing 12, there's an underflow here. So now, as there's an underflow here, we move one of these values down. So we have 10 down here. So after bringing 10 down, we fuse these two elements, and now this is the tree that we get. Now let's look at the subcase 3. In this, the parent node is a 2 node. So the subcases that we have discussed before, in that the sibling and the parent, first one was that sibling and the parent node both were 3 or 4 nodes. Second was when the parent was a 3 node, but sibling was a 2 node. Now the parent node is also a 2 node and the sibling is also a 2 node. So let's see, if we have to remove 14, 14 has got sibling 17 and 17 is just a 2 node. Its parent 15 is also a 2 node. So it satisfies both these properties of the subcase 3. And let's see what we can do here. We'll pull an item from parent to the empty node that we get after removing our element. So we remove 14 here, we get an empty node here. So we pull down 15, and then we'll fuse the siblings into one node. But there will be an underflow here. Hence, because of this underflow, this is a different subcase. But what we'll do is just simply repeat these steps, and these steps are similar to a subcase 2. So it's actually a subcase 2, nothing special, but we'll be just repeating these two steps. So we remove 14. It becomes an empty node here. After that, we remove 14. Now we pull down the parent here, 15. Fuse these two siblings into one node. But when we do that, as you can see, there's an underflow here. So what we'll do is again pull down the parent down here. So we'll pull down 11 here. So these two elements get fused into one, and the parent got pulled down here. Now again there's an underflow. But what we'll do is fuse these two siblings. So we fuse these two siblings, and this is the resulting tree that we get after removing 14. So with this, I've covered all the cases of deletion and all the subcases of that third part. And let's see with the conclusion what is the complexity of all these insertion deletion. Let's assume that our split, transfer and fusion that we did in our deletion takes over time. These are necessary for an insertion, but so as you saw, search took OH time, insertion also took O log n time, that is OH time, and deletion also will take O log n time as we have to move down the tree. So this brings us to the end of our video. Thank you so much for watching it.